In this video, we're going to start chapter 4 on cyclic subgroups, or cyclic groups in general, but we'll define first what a cyclic subgroup is. So we'll cover section 4.1. So we say, or we use this notation with angled brackets to say that we're looking at a set generated by that element. And what we mean by that is we're taking all powers of that element, where the powers can come from the integers. So this would include, of course, a to the first power, a squared, a cubed, and so on, but also a to the 0 power, which is the identity, and then a to the minus 1, so the inverse of a to the minus 2, the inverse of a squared, and so on. So we're calling that first a set generated by A, but of course we want to show that this is actually a subgroup of whatever group it comes from. So our first theorem here is that if A is an element of a group, then the group generated, or the set generated by A is a subgroup of G, and we'll call that the cyclic subgroup generated by A. Okay, so last time, at the end of chapter 3, we talked about the subgroup test, so let's remind ourselves of what that was. I'll just briefly recall it. So subgroup test, first is that the H, the thing that we're testing, is non-empty. That's the first thing we need. And also, whenever I pick two elements from H, if I form GH inverse, that also belongs to H. If these two things are true, then H is a subgroup. We use this little symbol with the less than or equal to sign, as H is a subgroup of G. Okay, so let's try this test here. So for the first part, of course, it's not empty because it contains A. So since A is in set generated by A, it is not empty. Of course, it has other things too, like the identity, but A could be the identity, so we can't say that there's more than one thing in it just yet. Okay, now the main part of the test. If we let two elements be in this set generated by A, then we know what elements look like in A. Every element is some power of A. Could be a negative integer, but either way, each element, so G is some power of A, say A to the M, and H is also some power of A to the N, for some M and N in the integers. So now we do the subgroup test. We form GH inverse. So GH inverse would then look like A to the M times A to the N inverse. But here we can use just our ordinary rules of exponents here. This would be minus n, and then we can add the exponents together. So this is A to the M minus n. And since m and n are integers, the difference between them is also an integer. So this does belong to the set generated by A. So we can have our conclusion that the set generated by A, or we'll be calling it from now on the subgroup generated by A, is a subgroup of G. And since we're using this word generated by A, we can call that element a generator of, or we call that element the generator. And of course, the whole group is cyclic if it is generated by some element. I've been using the word order a lot up until this point, probably sometimes incorrectly. But the order, so we'll give a real definition for order. is it is the smallest integer where if I take a to that power, I get back to the identity. And so we'll use this notation with the absolute value symbols for the order. So if the smallest power of a is n to get to the identity, then we'll say order of a is n. It's possible you have an infinite group and you have some elements that don't have such an integer. We say that the order is finite or infinite. Like for example, 1 in the integers, actually really any element in the integers, have infinite order because there's no way to add 1 to itself, or however many times you add 1 to itself, you're never going to get back to 0, which is the identity there. Next theorem, all cyclic groups are abelian. So remember what we need to show for abelian. If we pick two elements, we just have to show that if I multiply one way, I get the same as if I multiply the other way. And that abelianness, or the fact that it's commutative, will come from the fact that addition, when we use the rule for exponents, that is also commutative. So for our proof, we'll suppose G is a cyclic group. And we'll pick elements out of that group, G and H, and we'll show that if I multiply one way, G times H, I get the same as multiplying the other way, H times G. But first let's say, well, it's a cyclic group. By definition, it has some generator. So then G is generated by some element A, where A is in the group. Now let's let two elements, G and H, be in our group G. Then, just like before, we know what they look like. G looks like A to the M, and H looks like A to the N for some integers. Now let's look at the product one way. So GH would of course be A to the M times A to the N. Notice, we don't have to go back and prove, like I didn't say much up here, but you don't have to prove the rules for exponents because this notation just means multiplying A by itself M times, and this is multiplying A by itself N times. So we have a total amount of M plus N A's being multiplied together. So this really is A to the M plus N. But now we use the commutativity of addition to say, well, that's the same as A to the N plus M, and then split it up the other way. Even though this isn't complicated, I am kind of making it even more complicated. I could just say, well, that's M plus N copies of A. I can split that wherever I want. So here you split it with M first and then N, and here you split it N first and then N. Okay, so therefore, G is abelian. Next, we have a couple of statements that we'd like to either prove or disprove. And, try and get some intuition on them first before you decide which direction to go. Let's take a look at the first one. All of the generators of Z60 are prime. So certainly prime numbers would generate it. But all we really need is something relatively prime to 60 to generate Z60, or anything that's relatively prime to Z60 should generate it. So there are numbers between 0 and 59, because that's what Z60 is, that are relatively prime, that aren't prime themselves. although there's just one. Z60 is generated by 49. 49 is relatively prime to 60. 60 doesn't have 7 as a factor, and 49 only has 7 as factors. But I believe this is the only one. So it is false that all the generators are prime. If every proper subgroup of a group is cyclic, then G is a cyclic group. This one is one that might feel true, but this one's also false. And we've actually already seen a simple example of this. K4, the Klein 4 group. Let's remember what it is. That has the identity. It has the rotation. It's the symmetries of a rectangle, the vertical flip, and the horizontal flip. But all of the subgroups are, you can either have just the identity, you could have the identity with any of these other ones. But this is, the group generated by the identity. This is the group generated by R. We have two more. You have the identity with V is another subgroup, but that's the group generated by V. And also the identity with H is the group generated by H. But it is not cyclic. None of these elements, all these elements are of order 2. And so you would need an element of order 4 in order to generate the entire group. So K4 is not cyclic. So first two of these are false. This last one ends up being true, and this one is quite tricky. So a group with a finite number of subgroups is finite. So that is true, and it certainly feels true, but proving it is kind of tricky. Because what could happen, presumably, is you have finite number of subgroups, but the subgroups of themselves might be infinite or something like this. So what we need first is a little claim that if we have this case where you have a finite number of subgroups, then every element must have finite order. So we'll start with this little claim that every element has finite order. Okay, and we'll prove this by contradiction. So for the sake of contradiction, suppose you have an element of infinite order. Suppose x, or the order of x, is infinite. Well, we immediately get a contradiction because we can look at the cyclic subgroup generated by x, and then the cyclic subgroup generated by any of the powers of x. Then cyclic subgroup generated by x, cyclic subgroup generated by x squared, generated by x cubed, and so on, are all different subgroups, and there's an infinite number of them. Is an infinite number of subgroups, which is our contradiction. So we do have this claim that every element does have finite order. Now let's prove the main part, that the actual group is finite. So why we needed this claim is because we're going to focus on the cyclic subgroups in the group. So since the group, we're going to call it G, has finitely many subgroups, that's by assumption, then cyclic subgroups are just some of those subgroups, maybe all of them, but it would also have a finite number of cyclic subgroups. Let's give them names. Say subgroup generated by A1, subgroup generated by A2, but this list is finite, so eventually you get to an end, subgroup generated by AN. Now next, I want to say that G would be the union of all of these cyclic subgroups. So to prove that part, let's pick an element in G. So say let X be in G. Then I can just look at the cyclic subgroup generated by X. Well, that's all of them right there. So this must be on the list somewhere. So this is equal to AK for some. Okay. So every element in the group is contained in one of these cyclic subgroups. So if I take the union of them all, I get all of G. So this implies that G is the union of all of these cyclic subgroups. I from 1 to n. If you haven't seen this notation before, it's just our shorthand, like the big sum notation for just the union of a bunch of sets. But by our claim, every element has finite order, which means all of these cyclic subgroups have finite order as well. So I'm taking the union of a finite number of finite sets, so it must be finite. So by the claim, each subgroup generated by AI is finite, so that means G is finite. Again, it is a union of a finite number of finite sets. So again, even though the original statement seemed not that, or seemed somewhat obvious even, it does take a little bit to actually prove. Okay, the last couple of examples for this video in this section is to find the order of some elements in some groups. So first, find the order of 5 in Z12. Well, since 5 is relatively prime to 12, it should generate the whole group. And you could test that on your own. Just add 5 to itself, work mod 12, and you should get every number between 0 and 11. So the order of 5 is actually 12. Just to give you maybe some more interesting ones, if I wanted the order of 3 in Z12, just add it to itself until you get to 0. So 3 plus 3 is 6, plus 3 is 9, plus 3 is 12, but that's 0 mod 12. So you have to do 4 copies of 3 added together to get to 12. Now you might be thinking, oh, I just divide by 12, or 3 divided by 12 is 4. Well, not necessarily. We'll see exactly what you have to do. Like the order of 9, if you do 9 plus 9, you would get 18, but mod 12, that's 6. Add 9 again. You get 15, mod 12 is 3, and then finally add 9 again, you get 12, which is 0. So you also have to do 4 copies. So they actually have the same order. So it's not dividing, it's dividing by something. I believe the GCD. Here, sometimes we don't write, what the operation is if it's obvious. It's not always obvious. So here, this is the real numbers with addition. And over here, because of the star, this is complex numbers with multiplication. So square root of 3, if I add it to itself over and over again, you just get 2 root 3, 3 root 3. That's never going to come back to the identity in the real numbers, or the additive identity, which is 0. So the order of square root of 3 is infinity. But for negative I and the non-zero complex numbers under multiplication, so if you were to square it, you would get, let's make sure of this. Negative I squared is the same as I squared, right? Which is negative 1. Cubed should bring you back to I believe, and then finally to the 4th power should be 1. So the order of I is similar to the order of, order of negative I is the same as the order of I, which is 4. All right, so we'll stop there for this video. In the next video, we'll look at the next section, 4.2.